Hello and welcome to a series of videos that talk about differential equations. In the first of these videos, we're going to talk about approaching differential equations from an analytic point of view. But before we begin, let's talk about what a differential equation is. For starters, a differential equation is an equation that contains derivatives. Here are 1, 2, 3 different examples of differential equations. Notice that there's a dy dx or a d squared y dx squared in each of these equations, and therefore each one of those equations is a differential equations. They are the result of starting with a regular equation and taking its derivative. The middle one here is called a second order differential equation because it has second derivatives involved. We are very familiar with this because we have taken derivatives of many equations and the result is a differential equation. The big question of all differential equations is how do you solve them? In other words, where did we start with to get to this differential equation? The process of solving a differential equation is anti-differentiation. You're going backwards, right? So if I'm going to try to solve the differential equation, dy dx equals secant squared of x, then we're saying, well, what does y equal such that its derivative equals secant squared of x? Well, that's easy, I think. We know that secant squared of x is the derivative of the tangent of x, but it's also the derivative of the tangent of x plus 1, and the derivative of the tangent of x plus 2, and the derivative of the tangent of x plus negative 17, and whatever number we want to add, we'll call it a constant, doesn't affect its derivative. So therefore, we say that all the solutions are the tangent of x plus some constant c. You'll recognize this as the constant of integration when you find an indefinite integral. All right, so when we solve a second order differential equation, we're going to have to take the antiderivative twice. So let's give that a try with this next one. So remember that we know whether the second derivative of y with respect to x is 2 plus 6x. So if I wanted to figure out, I'm going to run out of space here, so I'm going to do it up here. If I want to figure out what dy dx is, that's going to be the first derivative. We have to take the antiderivative of the second derivative. So we're going to take the antiderivative of the 2x, or the 2. It's going to turn into 2x, right? The derivative of 2x gives us the 2. And we're going to have to take the derivative of the 6x, and then we're going to use that inverse power rule to say, well, x turns into x squared, but we have to divide by 2, so that 6 divided by 2 turns into a 3. But we're going to have a constant of integration. I'll stick it over here for fun. Now, this is still a differential equation, so if we're going to try to solve this differential equation, we still need to take the antiderivative one more time. So we're going to have a second constant of integration. So I'm going to go ahead and call this C1 in anticipation of a second constant of integration, namely C2. C1 is now going to be multiplied by some variable x, and the 2x is going to turn into, well, the x to the first is going to turn into x to the second. And we're going to divide the 2 by the new exponent of 2, so we'll get 2 divided by 2, which is 1. And same thing with this, the 3x squared is going to anti-differentiate to x cubed. And that would be the general solution for the second order differential equation. So this is not anything new, really. We're just taking antiderivatives. Normally, we'll see these first order antiderivatives. Therefore, we're going to be taking the antiderivative once and we'll be done. All right, now this third example of negative x over y is harder, right? Because we've got x's and y's in our differential equation. You might say, well, that's really tough. How in the world are we going to solve a differential equation? Well, if we have x's and y's in there. Remember, though, that we've seen derivatives that have x's and y's in the answer. We've seen those in implicit differentiation. So you might want to go back and review implicit differentiation if you're a little rusty on that. But what I'm going to do is I'm going to go back and I'm going to look at that first example, that tangent of x plus c. And I'm going to say, well, wait a second, our answer is y equals tangent of x. Why do we have a y equals there? Where did that come from? Well, let's think about what we did here. We Well, I said we took the antiderivative of dy dx. Well, that's not exactly what we did. We took the antiderivative with respect to x on the right side of the equation. Really what we did was we took this dx, which was in the denominator, and we moved it over to the other side. Think about this. If we multiply both sides of the equation by dx, then we're going to get dy all by itself on one side of the equation. And then secant squared of x is going to be multiplied by dx. Now that looks a little funny, but now if you think about this, think about what would happen if we took the antiderivative of both sides. Wait a second. The antiderivative of dy, well, the variable of integration here is y, so the antiderivative of dy is just y. Yeah, we could put a plus c there, but I'm not going to worry about putting a plus c on both sides of the equation. I'll just keep a plus c over here because it's easier to have one plus c instead of multiple plus c's, right? And of course, we know where this is going. The antiderivative of secant squared of x is obviously tangent of x. So we didn't worry about showing that middle step of separating the x's onto one side and the y's onto the other side because we didn't really need to. But in a situation like this next problem, well, this example 3 problem, I should say, where we have x's and y's mixed together, then we might want to consider this idea of trying to separate the x's and the y's from each other. So a differential equation is called separable if we can first write it in the form f of x plus or times g of y, okay, where f is some function of x and g is some function of y. If you take a look at this previous example, you don't see a g of y on the right side of the equation, but if we don't see a g of y, then we'll just call that g of y equal to 1. Who cares, right? Multiplying by 1 and nothing's going to happen. But on this next example, we do have a g of y that's something more interesting than 1, right? This is negative x times 1 over y. So my f of x is equal to negative x, and my g of y is equal to 1 over y. Why did I put the negative with the x? It's arbitrary. I just decided to. It's better to keep all of the stuff that we can with x and keep y as simple as possible. If you wanted to, you could put the negative with the y instead. I'm going to keep the negative with the x. At any rate, because we have a product of two different functions, right? We've got a product of negative x times 1 over y. Then it's easy to flip things around. And what do I mean by that? I mean, I'm going to flip the dx over to the other side by multiplying by dx. And I'm going to flip all of the stuff with y over to the other side by dividing by that function, by dividing by 1 over y. So if I do that, think about this. When we divide both sides by g of y, which is 1 over y, we're dividing by 1 over y. We're dividing by a fraction, which means we're multiplying by its reciprocal. So, right, dividing by 1 over y means multiplying by y. The dy that we had originally is going to get multiplied by y. And then the dx is going to be multiplied by my f of x, which is negative x. This process right here, basically we're multiplying both sides by dx, we're multiplying both sides by y. This process is called separation of variables. What we're doing is we're separating all of the y variables on one side of the equation with the dy in the numerator, and we're separating all of the x's onto the other side of the equation with the dx in the numerator. And when we do that with a dx in the numerator and a dy in the numerator, then we can anti-differentiate with, hopefully, relative ease. This is y to the first power, so we're going to anti-differentiate this to be y to the second power, inverse power rule, but we have to divide by that new exponent. And this is, whoops, not equals, excuse me, equals. And then this negative still sticks around, and this x was raised to the first power is going to change to the second power, and then we're going to divide by that new exponent. And we have to put a plus c in here. We could put a plus c on the left side and the right side, but why would we? We'll just put a plus c on one side. Again, we're always going to pick the x side to put the plus c on, just because it's the side we're more comfortable with. It's kind of arbitrary. And that is a version of the solution to the differential equation. It's not a very pretty solution, but one thing we could do, if we notice, well, I don't really like having fractions in my answer if I can help it. What if I were to multiply the left side and the right side of this equation by the common denominator of 2? Well, that would make things a little bit nicer, wouldn't it? We would have, instead of 1/2 y squared, we'd have 1y squared. Instead of negative 1/2 x squared, we'd have negative x squared. Instead of plus c, we'd have plus c. And now you're thinking, wait a second. If you multiply something by c, if you multiply c by 2, you don't get c, you get 2c, right? But remember what c represents. C represents any constant in the world. And if I multiply any constant in the world by 2, I get some new constant. It's true that this c and this c are not the same constant, but they are both constants. And in the realm of calculus, we really only care about whether things are constants versus variables. And so we'll just know that this is some other constant. And that would be another version of the solution to the differential equation. You might say, well, maybe I'd rather solve for y. Well, if I solve for y, that's something we could certainly do by taking the square root. But then we start having to worry about pluses and minuses, and that's not wrong, but we can do that. Another thing we could do is we could maybe add an x squared to both sides of the equation. And if we add x squared to both sides of the equation, then we're going to get x squared plus y squared equals c. And that is yet one more solution to this differential equation. Some might say this is the nicest form of the solution to this differential equation because of past experience and what we know that this set of equations looks like. More on that on the next video.